Hey, what's up, Chem Peeps? It's Mr. Boylan here for your very first free response practice video. For these types of questions, there are multiple parts, some of which may require earlier portions of the question in order to answer. It's important that you always show your work and that you always keep in mind significant figures. Let's do it! A student performed a laboratory exercise to determine the identity of an unknown metal. The data table below summarizes the information collected by the student throughout the lab. Step 1. Determine the mass of a dry, empty, graduated cylinder. Record in data table 1. Step 2. Place metal sample in graduated cylinder and determine combined mass of graduated cylinder and metal sample. Record in data table 1. Step 3. Empty the graduated cylinder. Step 4. Fill the graduated cylinder with 50.0 milliliters of water and record in data table 1. Step 5. Place the metal sample in the graduated cylinder with the water and record in data table 1. Let's take a look at the data. Boom! Part A. Show a numerical setup and calculate the following. Subpart I. The mass of the unknown metal sample. Alright, as you think about the procedural steps, think about what we also do in lab. We first determine the mass of an empty graduated cylinder and determine its mass to be 88.00 grams. Then we place the metal sample in that graduated cylinder and determine the total mass of the graduated cylinder and the sample, and determine that mass to be 116.00 grams. So, in order to determine the mass of the unknown metal sample without actually putting it on the balance, if you know the combined mass of the graduated cylinder and the sample and the empty graduated cylinder, simply subtract in order to determine the mass of the metal sample. Boom! Take a look at the work that I've shown. Even though it's a simple subtraction, you want to make sure that you're showing all of your work, and notice that I've taken into account significant figures. Subpart II, the volume of the unknown metal sample. Once again, think about the data in the table, and think about how you perform this in the lab. We first put 50.0 milliliters of water in an empty graduated cylinder. We're going to zoom in here so you can more clearly see what that volume is. 50.0, be mindful of how we use significant figures to read pieces of equipment in the lab. Next, we add our sample to the graduated cylinder. Notice what happens to the volume in our graduated cylinder. Oh, we've increased. This means that the combined volume of the 50 milliliters of water and the metal sample is now 53.1 milliliters. The difference in volume must be the volume of the added metal sample. Boom. Again, make sure you show your work, you're conscious of units, and significant figures. Subpart III, the density of the unknown metal sample. This is a classic example where you have to use a previous portion of the question to answer the one that you're on. It's important to note that even if your numbers from the earlier sections aren't correct, as long as you're using that information from the earlier sections in this current one, you can still earn full credit as long as you show your work. Recall that to solve for density, it's equal to the mass over the volume. I calculated the mass in part I calculated the volume in part II. A quick trip to my calculator. Remember, don't forget sig figs and units. Part B. Based on the information in data table 2 below, which of the following metals is most likely identity of the unknown? Remember that density is an intensive property. It can help us identify a substance. As I look at my calculated density of 9.0 gram per milliliter and compare that to the accepted densities in the data table, the most likely identity is going to be copper. Boom. I've answered my question using the data table. Keep in mind, if you've calculated your density incorrectly in A subpart III, as long as you're choosing an element based on the density you've calculated, you can still earn full credit. Part C, show a numerical setup using dimensional analysis and convert the volume of the metal sample determined in part A III from milliliters to fluid ounces. As with any dimensional analysis, I'm going to start with my known and I'm going to focus on my units. I start with milliliters, so I'm going to cancel that unit out on the bottom and first convert to liters. This is a metric conversion that you should know, and it's not provided in the problem. Next, I'm going to convert from liters to gallons using the provided statement of equality provided in the problem. Finally, I'll convert from gallons to fluid ounces using the provided statement of equality. Quick check to make sure all the units that I don't want cancel out and I'm left with the units that I do. Note that I didn't use all of the statements of equality. Sometimes you'll be provided with additional information that you don't need to solve the problem. Quick jump to my calculator. Boom. Once again, I'm keeping in mind sig figs and my units. Part D. In step 5 of the procedure, when the student placed the metal sample in the graduated cylinder with the water, some of the water splashed out. Would the calculated density of the metal sample increase, decrease, or remain the same? Mathematically, justify your answer. Let's go back and think about how we got the data in our data table. The mass of our metal sample isn't going to be changed by water splashing out of the graduated cylinder. That was determined before we added any water. However, the volume of our metal sample will be affected by water splashing out. If some of this water splashes out, so now there's less total final volume of water, we're going to calculate the volume of our metal sample to be less than what it is. So think about the formula for density and how that change in volume will affect the value of our density. Ideally, if no water had been splashed out, our volume would have been calculated correctly. However, because some of that water splashed out, our calculated volume is going to be much smaller than what it should be. Again, the mass values will remain the same. So when the numerator value in our density equation is constant, but the denominator volume value decreases, the value of our density is going to increase or become greater. So in my answer, the calculated density will increase. You want to be sure to answer the question. Increase, decrease, or remain the same. A smaller measured volume of metal will result in a larger calculated density. Here is my mathematical justification in formula format and in word format. Finally, part E. After completing the experiment as outlined above, the student cut the metal piece in half. Will the density of the cut metal pieces be smaller, larger, or equal to the density of the original metal sample? Explain. All right, as we think about this, imagine my original metal sample, and imagine I had that exact same metal sample, but cut into 2 halves. Think about what's going on with density for the sample I'm going to circle here in red. The density for that larger piece, our mass may be, let's say, 10 grams, just to make the math easy, and the volume, 10 milliliters. So the density would be 1 gram per milliliter. For the half sample, notice that its mass has decreased, but its volume has also decreased by half. So the density remains constant. Remember, density is an intensive property and will not change depending on how much matter you have. It's one of the reasons we're able to use density to help us identify the material. All right, so as always, be sure to answer the question. The density of the cut metal will be equal to the density of the original metal sample. So make sure that you're answering that question. Density is an intensive property and will therefore remain constant regardless of sample size. All right, that does it for this video. Hope you're feeling a little better about the free response on our exam. Have a fantastic day.